I'm going to show you the real differences between 4WD, AWD, FWD, and RWD that will help you choose the perfect drivetrain and free you from the confusion and marketing hype so you never have to wonder which one is best for you again. All without needing a degree in engineering. Once you understand how each system works, then you'll be able to drive smarter in any condition and you'll never have to second-guess your choice or get stuck with the wrong setup. So after you know how to compare control, agility, and fuel efficiency, you'll go from uncertain to confident without wasting money. And that's when you'll truly enjoy your drive. And when you know how to pick the right drivetrain, you'll be able to get the best performance for your needs, which will free you to drive with total confidence. When discussing drivetrains, there are several common beliefs that deserve examination. Popular wisdom suggests that four-wheel drive excels in off-road scenarios. Rear-wheel drive offers the easiest maintenance. Front-wheel drive delivers the best fuel economy, and all-wheel drive provides superior control across various conditions. Each drivetrain configuration demonstrates distinct characteristics in several key performance areas. Four-wheel drive shows impressive control and stability, but struggles with fuel efficiency. Four-wheel drive systems offer unique flexibility, as many can be engaged or disengaged based on driving conditions, which helps conserve fuel when additional traction isn't necessary. This drivetrain particularly shines in challenging off-road environments, demonstrating superior performance in mud, sand, and rocky terrain. The ability to lock front and rear axles together provides maximum grip in extreme conditions. However, the system's added weight reduces fuel efficiency, and its complexity leads to higher maintenance costs. All-wheel drive stands out with exceptional ratings across control, stability, and moderate scores in repair costs and fuel economy. All-wheel drive functions like an intelligent co-pilot, continuously monitoring road conditions and distributing power to the wheels that require it most. This system typically operates continuously, making it extremely user-friendly. It provides exceptional traction in adverse weather conditions and enhances control during acceleration and cornering. Performance car manufacturers increasingly favor AWD for its superior power distribution capabilities. The drawbacks include higher repair costs, reduced fuel efficiency compared to FWD and RWD, and less robust off-road capabilities than 4WD. Front-wheel drive excels in fuel economy and maintains solid scores in agility and repair costs. Front-wheel drive represents the most common drivetrain in passenger vehicles, featuring an engine that powers the front wheels. Its lighter and simpler design contributes to superior fuel efficiency and affordability. FWD offers predictable handling characteristics that benefit novice drivers. However, this configuration tends to understeer in sharp turns or wet conditions and presents less balanced weight distribution, which affects handling dynamics. It also proves less suitable for high-performance or off-road applications. Rear-wheel drive achieves top marks in agility while maintaining balanced performance across other metrics. Rear-wheel drive, favored in sports cars and luxury vehicles, delivers power to the rear wheels and offers balanced weight distribution that enhances agility and steering feedback. This configuration appeals to performance enthusiasts, particularly for activities like drifting and spirited driving. The improved weight distribution enhances cornering capabilities. However, RWD presents greater challenges in slippery conditions, carries more weight than FWD systems, and typically incurs higher manufacturing and repair costs. In conclusion, each drivetrain configuration serves specific driving needs optimally. Four-wheel drive remains unmatched for extreme off-road adventures. All-wheel drive provides the most reliable performance in varied conditions throughout the year. Front-wheel drive offers the best solution for daily commuting and cost-effectiveness. Rear-wheel drive delivers the most engaging driving experience for enthusiasts. The optimal choice ultimately depends on individual requirements, environmental conditions, and personal driving preferences. If you're a car owner who truly cares about agility and making sure your vehicle responds precisely to every turn and maneuver so you can experience the thrill of confident sharp handling in any driving scenario. I'll share all you need to know about drivetrain agility. Agility, in the context of driving, refers to a vehicle's ability to change direction quickly and maintain stability while doing so. This is affected by how the drivetrain distributes power, how the differentials function, and how many wheels are actively involved in propulsion. Each system has its strengths and weaknesses, which stem from the way power is managed and how the vehicle interacts with the road surface. Starting with four-wheel drive, or 4WD, is mechanically similar to AWD in that all four wheels receive power, but the way this power is distributed is fundamentally different. Traditional 4WD systems rely on a transfer case instead of a center differential, meaning power is split evenly between the front and rear axles when engaged. Most modern 4WD systems are part-time, allowing the driver to switch between two-wheel drive, typically RWD, and 4WD as needed. Because the front and rear wheels turn at the same rate in 4WD mode, cornering can be less fluid on paved roads, as the drivetrain resists the natural tendency for the inside and outside wheels to rotate at different speeds. This resistance can cause binding or hopping in tight turns, reducing agility in everyday driving situations. While 4WD shines in off-road environments where traction is the priority, it does not enhance agility on dry pavement in the way AWD or RWD can. The lock power split means there is no real-time torque adjustment to optimize cornering performance, making 4WD less suited for precision handling. All-wheel drive, or AWD, aims to blend the advantages of both FWD and RWD by dynamically distributing power between all four wheels. The drivetrain typically consists of three differentials: a front, a rear, and a center differential. The center differential, or in some cases, an electronically controlled clutch or torque vectoring system, determines how much power is sent to the front versus the rear. Some AWD systems favor FWD under normal conditions, but can redirect power to the rear wheels when traction is needed. Others maintain a more balanced power split at all times. This constant adaptability enhances agility by ensuring that power is always sent to the wheels with the most grip. During sharp cornering, AWD minimizes both oversteer and understeer by adjusting torque distribution in real time. This makes AWD vehicles feel more stable and planted, especially when sudden maneuvers are required. However, the added complexity of AWD systems can introduce slight delays in power delivery compared to RWD, and the extra weight of additional drivetrain components can slightly dull overall responsiveness. Front-wheel drive, or FWD, takes a different approach. In this layout, power is sent exclusively to the front wheels through a transaxle, which typically combines the transmission and differential into a single unit. The front differential allows the two driven wheels to rotate at different speeds, which improves stability during cornering. Unlike RWD, where the rear wheels push the car forward, in FWD, the front wheels pull the vehicle. Because most of the car's weight, including the engine, is over the driven wheels, traction remains stable even in less than ideal conditions, such as rain or light snow. From an agility standpoint, FWD vehicles exhibit safe, predictable handling characteristics. They tend to understeer, meaning the front wheels lose grip before the rear, making it less likely for the rear to slide out unexpectedly. However, since the front wheels are responsible for both steering and propulsion, their grip can be overwhelmed when attempting aggressive turns at high speed. This can lead to reduced cornering sharpness compared to RWD, making FWD vehicles generally less agile when it comes to performance driving. In terms of pure agility, RWD provides the most natural and engaging cornering dynamics, allowing for sharper turn-in and better weight balance. AWD follows closely with its ability to adjust power dynamically, improving stability and responsiveness, though at the cost of some added weight and mechanical complexity. FWD is safe and predictable, but inherently limited by the fact that the front wheels must handle both steering and power delivery, making it more prone to understeer. 4WD, while excellent for rugged terrain, is the least agile in on-road driving due to its locked power distribution and lack of adaptability in high-speed cornering. Rear-wheel drive, or RWD. This setup is often associated with performance vehicles and sports cars. In RWD vehicles, power from the engine is directed exclusively to the rear wheels via a drive shaft and a rear differential. The rear differential is responsible for allowing the two rear wheels to rotate at different speeds when cornering, which prevents wheel slip and maintains traction. Because the front wheels are not involved in propulsion, they are free to focus entirely on steering. This separation of duties allows for precise turn-in response and a more natural weight balance. The effect is a lively, responsive feel that gives the driver a heightened sense of control, especially at higher speeds. However, RWD vehicles can become tail-happy if too much throttle is applied mid-turn, as power to the rear wheels can overcome available grip, causing oversteer. While skilled drivers can use this to their advantage for sharper cornering, it requires experience to control effectively. For drivers looking for the most agile option in a sports car or performance vehicle, RWD remains the top choice due to its precise handling characteristics. Those who want a balance between agility and all-weather capability may find AWD to be the best compromise. FWD vehicles, while not the sharpest handlers, provide confidence and stability in everyday driving. Meanwhile, for WD is ideal for those prioritizing off-road capability rather than nimble cornering. Ultimately, choosing the right drivetrain depends on personal driving preferences and the conditions in which the vehicle will be used. A well-informed buyer can leverage this understanding of agility to select the drivetrain that best suits their needs, whether it be for spirited driving, all-weather stability, or adventure off the beaten path. We're here to show you how different drivetrains perform, how they handle, how they grip, how they respond in real-world conditions. And once you see the results, you can decide what matters most. When it comes to vehicle stability, the drivetrain plays a crucial role. It determines how power is delivered to the wheels, how a car reacts to turns, acceleration, and sudden maneuvers. Four major drivetrain configurations influence stability: four-wheel drive for WD, all-wheel drive AWD, front-wheel drive FWD, and rear-wheel drive RWD. Each of these systems distributes power differently, affecting how the vehicle grips the road, handles corners, and responds to external forces such as road conditions and driver input. Starting with four-wheel drive, or 4WD. This system is traditionally designed for off-road use in challenging terrains. Power is typically sent to all four wheels, but often through a selectable system, meaning the driver can choose between two-wheel drive and four-wheel drive modes. The key component in 4WD is the transfer case, which directs power evenly to both the front and rear axles. Most 4WD vehicles use a solid rear axle and either a locking or limited slip differential to manage power distribution. Since 4WD operates by locking the front and rear axles together, it excels in off-road conditions where stability is measured in terms of traction over uneven surfaces. However, when used on dry pavement, the locked axles create binding in turns, reducing agility and stability in high-speed maneuvers. The inability of the system to differentiate wheel speeds between the front and rear in standard 4WD mode can lead to understeer or unpredictable handling, making it less stable at high speeds or during quick directional changes. All-wheel drive, or AWD, differs from 4WD in that it continuously sends power to all four wheels without requiring driver input. Most modern AWD systems use an electronic center differential or a multi-plate clutch system to dynamically allocate power between the front and rear axles. This ability to shift power based on traction needs provides a significant stability advantage in varying road conditions. Because AWD vehicles can transfer torque between the front and rear in real time, they maintain better grip during acceleration and cornering. This results in superior stability on wet, icy, or loose surfaces compared to 4WD and other drivetrains. Additionally, many AWD systems use torque vectoring, which can send more power to individual wheels to enhance cornering stability. The continuous power distribution prevents sudden traction loss, making AWD one of the most stable drivetrains for everyday driving in unpredictable conditions. However, because AWD vehicles are often heavier due to extra drivetrain components, their weight distribution can sometimes reduce overall agility compared to lighter FWD or RWD counterparts. Front-wheel drive, or FWD, is one of the most common drivetrains in passenger vehicles. It operates by sending power exclusively to the front wheels through a single differential, which splits power between the left and right front wheels. Because the engine and transmission are both located at the front, FWD cars have a front-heavy weight distribution, which significantly impacts stability. Under normal driving conditions, FWD offers predictable and stable handling, especially in straight-line driving and mild turns. The front wheels pulling the car forward create a natural tendency for the vehicle to maintain its path, which enhances stability in everyday driving. However, under hard acceleration or aggressive cornering, FWD vehicles are prone to understeer, meaning the front wheels lose grip first, causing the vehicle to push wide in turns. This can reduce stability at high speeds or when navigating sharp corners. Additionally, since the rear wheels are not powered, they provide no assistance in maintaining directional stability under acceleration, making FWD less stable than AWD in low traction conditions. Rear-wheel drive, or RWD, operates by sending power to the rear wheels through a rear differential, which divides power between the left and right rear wheels. This configuration provides a balanced weight distribution since the drivetrain components are more evenly spread between the front and rear of the vehicle. Stability in RWD vehicles largely depends on their ability to maintain traction while cornering and accelerating. Unlike FWD cars, which pull the vehicle forward, RWD cars push from the rear, which can improve high-speed stability and handling precision. This is why sports cars and performance-oriented vehicles favor RWD. However, RWD cars are more prone to oversteer, meaning the rear wheels can lose traction and cause the back end of the car to slide out. This makes RWD vehicles less stable in slippery conditions such as rain, snow, or ice, especially without electronic stability control. Because the rear wheels are responsible for both propulsion and directional changes, they require greater driver skill to maintain stability in emergency maneuvers. Comparing these drivetrains strictly from a stability perspective, AWD offers the most consistent and reliable stability across a variety of driving conditions. Its ability to dynamically adjust power distribution minimizes sudden traction loss and enhances control in inclement weather. 4WD, while excellent for off-road stability, is less stable at high speeds and on dry pavement due to its rigid power distribution. FWD provides good stability in everyday driving but struggles with high-speed cornering stability due to its front-heavy nature and understeer tendencies. RWD delivers excellent stability in high-speed and performance driving, but is more prone to instability in slippery conditions due to oversteer. Understanding these stability characteristics helps drivers choose a drivetrain that best suits their driving environment and skill level. So let me ask you something. How important is it for you to finally feel in complete control behind the wheel? How badly do you want to navigate any road condition with confidence, without second-guessing your vehicle's capability? And what would it mean to you to make the right choice for your driving needs? Let's break down four-wheel drive, 4WD, all-wheel drive, AWD, front-wheel drive, FWD, and rear-wheel drive, RWD, exclusively based on how they impact vehicle control. 4WD systems use a transfer case to split power between the front and rear axles, often at a fixed 50-50 ratio. Unlike AWD, 4WD is typically manually engaged, locking power distribution for challenging conditions. Many 4WD vehicles have locking differentials, allowing even power delivery to all four wheels when needed. With locked differentials, 4WD vehicles maintain control even when some wheels have little to no traction. Because 4WD locks the front and rear axles together, it can create resistance in turns, binding, and reduce agility on paved roads. Many 4WD systems require manual activation and deactivation, meaning drivers must decide when to engage the system for optimal control. 4WD is ideal for extreme conditions, such as deep snow, mud, or rock crawling, but is not as useful on dry pavement due to binding effects. It demands a higher level of driver input and is best suited for those who need dedicated off-road capability. AWD systems vary widely, but they typically distribute power to all four wheels through multiple differentials, often one at the front, one at the rear, and a center differential or electronically controlled coupling. Power distribution can be fixed or variable, shifting power to different wheels based on traction needs. AWD continuously monitors traction and redistributes power to maintain grip, making it excellent for wet, snowy, or mixed condition driving. Because power shifts between axles as needed, AWD vehicles exhibit more neutral handling characteristics compared to FWD or RWD. Some AWD systems are front-biased like FWD-based AWD, while others are rear-biased like Performance AWD, affecting how they respond under power. AWD enhances control in unpredictable conditions, making it a great choice for safety and confidence. However, not all AWD systems are the same. Some provide near-instant response, while others have lag due to electronic engagement mechanisms. AWD does not guarantee invincibility. Excessive speed or poor tire choice can still compromise control. FWD vehicles send engine power to the front wheels, which handle both steering and propulsion. A single differential, typically located within the transaxle, splits torque between the two front wheels. Most FWD cars use an open differential unless equipped with traction-enhancing mechanisms like limited slip differentials, LSD, or electronic torque vectoring. Because power is directed to the front wheels, FWD cars tend to push forward rather than rotate into a turn when traction is lost. This is called understeer, a predictable and generally safe characteristic, especially for inexperienced drivers. With more weight over the driven wheels, due to the engine's position, FWD vehicles perform relatively well in rain or light snow, enhancing stability. Since the rear wheels are passive, not powered, they provide little influence on directional control, making FWD vehicles prone to reduced rear stability under hard braking or sudden maneuvers. FWD vehicles are easier to control in low-traction situations, but can struggle under high acceleration, where torque steer, a pulling sensation to one side under power, becomes noticeable. They are also less balanced in aggressive cornering, making them less ideal for performance driving. RWD cars send power to the rear wheels through a drive shaft connected to a rear differential. This differential distributes power between the two rear wheels and can be an open, limited slip, or electronically controlled LSD, depending on the vehicle. Unlike FWD, RWD vehicles can lose traction at the rear when power is applied aggressively in turns. This oversteer tendency allows for more dynamic control but requires skill to manage. By separating the power source from the driven wheels, RWD cars maintain a more even weight balance between front and rear axles, improving handling responsiveness. RWD vehicles tend to track better at higher speeds, making them ideal for sports cars and performance vehicles. RWD requires more attention, especially in slippery conditions where a loss of rear traction can lead to fishtailing. However, it provides superior handling characteristics in dry conditions, making it favored for enthusiast driving and performance applications. Fuel economy isn't just about engine size or aerodynamics. Your car's drivetrain plays a major role. Whether it's four-wheel drive, 4WD, all-wheel drive, AWD, front-wheel drive, FWD, or rear-wheel drive, RWD, the way power is distributed to the wheels affects how efficiently fuel is used. Some systems demand more energy, while others maximize efficiency. To understand why, we need to look at how power is transferred, how many wheels are driven, how differentials function, and where mechanical losses occur. Starting with four-wheel drive, this system is designed primarily for off-road or rugged terrain. A traditional 4WD vehicle uses a transfer case, which splits power between the front and rear axles equally when engaged. The system often includes two differentials, one on each axle, and in some cases, a locking center differential or a transfer case that acts as one. The key reason 4WD vehicles tend to have lower fuel economy is that they are built with heavy-duty components to endure rough conditions. These components add weight, which requires more energy to move. Additionally, the drivetrain creates mechanical resistance since power must travel through additional gears and shafts, increasing friction and energy loss. In most vehicles, 4WD is not constantly engaged, meaning that in standard driving conditions, the front or rear wheels operate alone. However, even when disengaged, the extra drivetrain parts still add weight and resistance, contributing to reduced fuel efficiency. All-wheel drive functions differently from 4WD because it operates continuously or automatically engages when necessary. An AWD system can have a variety of configurations, but in most cases, it employs three differentials, one on the front axle, one on the rear axle, and a center differential that manages the power split between the front and rear. Some AWD systems use a multi-plate clutch or viscous coupling instead of a traditional center differential to transfer power as needed. The constant engagement of AWD increases fuel consumption compared to two-wheel drive systems because the drivetrain is always active, requiring additional power to turn the extra components. More moving parts mean greater mechanical drag and energy loss. However, AWD systems also improve handling and stability, particularly in wet or snowy conditions, by automatically distributing torque to the wheels that need it most. This agility can help drivers maintain control, but the trade-off is higher fuel usage due to the continuous operation of all four wheels. Front-wheel drive is generally the most fuel-efficient drivetrain because it has the simplest and lightest mechanical layout. In an FWD vehicle, the engine sends power directly to the front wheels via a single differential housed inside the transmission. Since power doesn't have to travel through additional components like a transfer case or rear differential, less energy is lost through friction. The absence of extra driveshafts and differentials also reduces the vehicle's overall weight. Another advantage of FWD is that it places more weight over the front wheels, increasing traction in slippery conditions without the need for a power-hungry AWD system. Because FWD layouts are mechanically simple, they allow for better fuel economy by reducing drivetrain loss. However, since only the front wheels are responsible for both propulsion and steering, FWD vehicles can suffer from torque steer, a tendency for the car to pull to one side under hard acceleration. This issue does not directly affect fuel efficiency, but is a characteristic of FWD that distinguishes it from other drivetrains. Rear-wheel drive, by contrast, sends power to the rear wheels, typically through a drive shaft connected to a rear differential. RWD systems are common and performance-oriented in larger vehicles because they offer better weight distribution and handling dynamics. However, from a fuel economy standpoint, RWD is usually less efficient than FWD. The primary reason for this is that the power must travel a longer distance from the engine at the front of the car, in most cases, to the rear wheels. This means additional mechanical losses occur through the drive shaft and differential. While RWD does not suffer from torque steer like FWD, it does require extra reinforcement in the drivetrain to handle power delivery, which adds weight and increases energy consumption. Additionally, since most of the vehicle's weight sits over the front axle while the driving wheels are at the rear, RWD vehicles typically have less traction in slippery conditions compared to FWD. This can lead to reduced efficiency in stop-and-go traffic, where traction control systems may need to intervene more frequently, using extra energy. Comparing these drivetrains strictly on fuel economy, FWD comes out on top due to its lightweight, efficient design, and minimal power loss. RWD follows, as it still only drives two wheels, but has slightly greater energy losses due to its longer power transfer path. AWD consumes more fuel than either two-wheel drive option because it engages more drivetrain components more frequently. 4WD is the least fuel-efficient system, as it is designed for off-road durability rather than everyday efficiency. The choice between these drivetrains ultimately depends on a driver's needs. Those prioritizing fuel economy should consider FWD, while those needing better traction in all conditions might accept the fuel penalty of AWD. RWD suits those who value balanced handling and performance, though at a slight fuel efficiency cost, while 4WD is best reserved for those who genuinely need off-road capability and are willing to trade efficiency for ruggedness. We're here to show you the real impact of different drivetrains, how they perform, how they wear, and what that means for your wallet when repairs are needed. Because when it comes to vehicle maintenance, the drivetrain isn't just about performance, it's a major factor in the complexity and cost of repairs. And once you see the differences, you can decide what matters most. The four main drivetrains: four-wheel drive, 4WD, all-wheel drive, AWD, front-wheel drive, FWD, and rear-wheel drive, RWD, each have different mechanical configurations, which directly impact the repair process. Understanding these differences can help car owners make informed decisions about their vehicles, especially in terms of long-term maintenance and associated expenses. Four-wheel drive, 4WD systems are designed primarily for off-road use, featuring a robust power distribution mechanism. Power from the engine is transferred through a transfer case, which splits torque between the front and rear axles. The vehicle typically has two differentials, one at the front and one at the rear. In more advanced 4WD systems, a center differential or locking mechanism allows all four wheels to move at the same speed when traction is low. Because 4WD vehicles often operate under extreme conditions such as rough terrain, deep snow, or mud, their driveline components experience significant wear and tear. Repairs on a 4WD system can be costly due to the heavy-duty nature of the components. Issues often arise with the transfer case, which contains complex gears that require precise calibration. Additionally, because 4WD systems usually include locking hubs and additional mechanical parts, failures in these areas can lead to expensive repairs. When one part of the system fails, there's often a cascading effect where related components also suffer damage, increasing the overall repair bill. All-wheel drive, AWD, systems are engineered for on-road agility, automatically distributing power between the front and rear wheels for optimal traction. Unlike 4WD, AWD systems do not require driver intervention to engage, as they use electronic sensors and clutches to shift power dynamically. AWD vehicles typically have three differentials: front, rear, and center. The center differential plays a crucial role in adjusting power between the axles based on real-time driving conditions. The complexity of AWD drivetrains means that maintenance and repairs can be expensive. AWD vehicles often feature intricate electronic controls, multi-plate clutches, and advanced sensors that require specialized diagnostic tools. One common issue with AWD systems is the wear of the center differential or viscous coupling, which can lead to uneven power distribution and unpredictable handling. Because all four wheels are constantly engaged to some degree, tires wear down more quickly, and drivetrain components experience greater stress, leading to more frequent replacements of axles, CV joints, and differentials. Additionally, fluid changes for the differentials and transfer case are critical, and failure to perform regular maintenance can result in expensive internal damage. Front-wheel drive, FWD, vehicles are the most common and typically the least expensive to repair. In a FWD setup, the engine directly powers the front wheels through a transaxle, which combines the transmission and differential into one unit. Since all power is concentrated at the front, there is only one differential, simplifying the drivetrain. The primary advantage of FWD systems in terms of repairs is their relative simplicity. With fewer moving parts compared to 4WD and AWD, there is less wear and a lower likelihood of drivetrain-related failures. However, FWD vehicles place significant stress on the front tires, axles, and constant velocity, CV joints, as these components must handle both power delivery and steering. CV joint failure is a common issue in FWD vehicles, usually resulting from torn protective boots that allow dirt and moisture to degrade the joint. While repairs to CV joints are not as costly as fixing AWD or 4WD systems, neglecting them can lead to total axle failure, which is more expensive to replace. Another potential problem with FWD systems is torque steer, where uneven power distribution can cause the vehicle to pull to one side under hard acceleration, which, over time, can lead to premature wear of steering components. Rear-wheel drive, RWD, systems distribute power to the rear wheels through a drive shaft connected to the transmission. The rear differential controls power distribution between the left and right rear wheels, while the front wheels handle steering exclusively. RWD vehicles tend to have a simpler design than AWD and 4WD systems, but require a longer drive shaft and a rear differential, both of which are susceptible to wear. One of the most common repair issues in RWD vehicles is differential wear, particularly when fluid changes are neglected. The differential contains gears and bearings that require proper lubrication to function smoothly. Over time, worn differential components can lead to noise, poor performance, and costly rebuilds. Another common issue in RWD vehicles is universal joint, U-joint, failure, which affects the drive shaft's ability to transmit power efficiently. If a U-joint fails, the drive shaft can detach, leading to severe mechanical damage. While RWD vehicles generally have fewer drivetrain components to repair than AWD or 4WD vehicles, their rear-heavy power distribution puts extra strain on the rear suspension, axles, and tires, leading to more frequent replacements. Comparing these drivetrains exclusively from a repair standpoint, FWD is the least expensive to maintain due to its simpler design and fewer components. RWD is slightly more complex, but still cheaper to repair than AWD or 4WD, with differential maintenance being the primary concern. AWD and 4WD systems are the most expensive to repair due to their additional differentials, transfer cases, electronic components, and more frequent wear of drivetrain parts. While AWD provides agility and convenience for daily driving, it also involves expensive components such as electronic sensors and clutches that require specialized servicing. Meanwhile, for WD vehicles designed for rugged terrain, demand frequent maintenance on their transfer case and differentials, leading to high long-term costs. Ultimately, the choice between 4WD, AWD, FWD, and RWD should consider not only driving needs but also repair costs and maintenance expectations. A driver who primarily commutes on paved roads with occasional adverse weather may find FWD or AWD more practical in terms of repair costs. Conversely, those who frequently drive on rough terrain may accept the higher repair costs of 4WD for the sake of superior off-road capability. RWD offers a balance between durability and performance, though it may require occasional repairs related to the differential and drive shaft. In all cases, regular maintenance, such as differential fluid changes, CV joint inspections, and transfer case servicing can help minimize unexpected repair costs and extend the life of the drivetrain.